Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at a short position paper that was published back in the 2017 proceedings of the Hot Topics in Operating Systems. And this takes a look at the question of how the Linux kernel is going to adapt to a world in which serverless loads become more and more common. It started with the bare kernel, and then there was a phase where a lot of the kernel abstractions were ill-suited to cloud workloads and got bypassed via various frameworks or by virtualization. And then we arrived at containers. But the authors in this paper are making the case that even containers are not a good abstraction for serverless. The authors in this paper are predicting that the rise of serverless will mean the fall of Linux. The authors make this prediction based on two major trends. The first one is that the complexity of the Linux kernel is growing unabated over time, and the second one is that the unit of execution in the cloud is shrinking. It started with full virtual machines, then we went to smaller containers, and now it is these tiny functions that are executed based on an event-based model. There has been some research that showed that the kernel's complexity has been growing quadratically over time. What do we need from a platform that is well suited to serverless workloads? The first one is security and isolation. You obviously have code running from multiple tenants, and they must be isolated from each other. The second big requirement is that these serverless actions must perform well. And what we mean here by performance is two things. The first one, of course, is low latency. As these actions are executed on an event-based model, we want that execution to happen very quickly. The second performance requirement is high throughput, because the number of actions that run on a machine must be able to pay the cost of that machine, even if the actions are extremely short-lived. They did some back-of-the-envelope calculations compared to the price of an Amazon EC2 instance and arrived at the figure of needing about 125 actions per second with Lambda serverless functions in order to break even with the cost of the underlying EC2 instance. At a very high level, there are three ways you could go about designing a native platform that supports serverless workloads. The first one is to simply keep extending Linux to meet serverless requirements, just the way it was extended for virtualization, just the way it was extended for containerization. The second option bypasses the parts of the Linux kernel that you don't need. This is similar to the approach taken by frameworks like DPDK or SPDK that roll their own storage or networking abstractions. And finally, the most radical option is to build a new kernel from the ground up that is suited for serverless. There are two main trade-offs to think of as you go about this design choice. The first trade-off is how familiar you are with the abstractions that this kernel provides. In the first option, obviously, you're familiar with the abstractions of the existing kernel, whereas in the last one, these are all new abstractions. The second trade-off is how much the complexity of the solution is. Again, in the first one, there's going to be a lot of complexity because you're extending an already complex Linux kernel with a lot of new capabilities specifically for serverless loads. Whereas in the last option, which is tailor-built for this purpose, the complexity, hopefully, will be much lower. We keep talking about how complex the Linux kernel is and how ill-suited it is for serverless workloads, so let's get into a little bit more detail on that point. There are large parts of the kernel that are simply not necessary for serverless workloads. For example, a lot of complexity in the kernel has to do with optimal scheduling under heavy competing workloads. In serverless, you have very short-lived actions, and you want them to be non-interruptible and go to completion. This means you could use a drastically simpler scheduler. Again, Lambda functions accept one input at startup and provide their output on completion, which means the set of I/O related infrastructure that they need is very simple and very limited. They don't need files or networking or all the hundreds of syscalls related to I/O in the Linux kernel. Lambda functions are also isolated from each other, so you don't need any inter-process communication. And finally, they do not share data with other Lambda functions, so you do not need any synchronization primitives. So this should just give you an idea of how much of the machinery and complexity of an existing kernel, of an existing general purpose kernel, a serverless workload simply does not need. What about using containers? According to the authors, containers do not perform well enough to meet this use case, both in terms of latency as well as throughput. The one architecture that does come close to meeting these needs is to have a unikernel. They did some simple experiments using a very simple Hello World workload, so that all you're really testing is the overhead of the underlying infrastructure. And they ran it in 3 different scenarios. One is straight on the kernel, the second was inside a container, and the third one is in a unikernel. And what they found with their quick benchmarks was that containers have a 6x to 8x overhead when it comes to the latency of starting up, as well as the throughput in terms of how many actions you can perform per second. So what this comes down to is a very strong case for preferring unikernels over containers. However, you have to realize that unikernels have their own trade-offs in terms of development complexity. This paper was written a couple of years before the Firecracker VM paper that describes the virtual machine architecture that Amazon uses for their Lambda service. And what the authors in that paper did was to use a very lightweight virtual machine and not a container. But their virtual machines were lightweight enough to satisfy the performance requirements for serverless workloads. So that's another interesting point in this design space. But all the same, even if we build a very custom platform for serverless workloads, Linux is not leaving the data center. It will still remain very active in what the authors call the role of a control plane. This means the Linux kernel is what orchestrates all the workloads within a machine, how those actions are queued and coordinated among different cores. So that was a quick look at a paper that looks at some of the design considerations that we need to think about when looking at this new era of serverless workloads in the data center. I hope you enjoyed that, and I will see you next time. Thank you very much.